Shall we start for the first talk today on the topic of the automatic segmentation of polycystic kidneys from magnetic resonance images using a three-dimensional fully conventional network from Dr. Jamie O'Reilly, College of Biomedical Engineering, Rangsit University. Please welcome him. Okay, now Dr. Jamie, you can share your slide. Okay.
Okay, I'm trying to. Okay. Can you see?
Yes.
Yes, got it.
Okay, good morning, everyone. So thank you for the introduction, Dr. Piscini. And this project is about automatically segmenting the kidneys, polycystic kidneys from the MRI images. And this is a collaborative project between doctors at Ramatabadi Hospital and us engineers at College of Biomedical Engineering, Rangsit University. So here are two example images of patients with polycystic kidney disease. And so you can see the one on the left, the kidneys look fairly normal. There's a small cyst seen in the liver here. But on the right-hand side, there's a severe case of polycystic kidney disease. So believe it or not, this is the kidney tissue here, and the liver also contains many cysts. So to monitor this disease, what the doctors have to do is during their practice, they have to analyze every image in an MRI scan and draw the contour around the kidneys. Okay, so cases where the kidneys look normal might be quite quick to draw around, but cases where there's a severe cyst load are difficult for the doctor to actually draw the kidney contour. So it's time-consuming and laborious task. So our objective in this research is to automatically segment the kidneys and to calculate the kidney volume. So when we've segmented the kidneys, it's quite a straightforward calculation to estimate the total kidney volume. We just compute the area for each kidney in each slice or frame, and then multiply that by the slice thickness. Okay, so to start the project, okay, we're using the 3D fully convolutional network, right? So it's supervised learning in machine learning speak, and we have to have a label, or in this case, we can call it a mask. So on the right-hand side here, you can see a binary segmentation mask where all of the background tissues are 0 value or black, and the pixels that contain the kidney in the MRI scan are labeled 1 or white in this image. So the model will try to learn the relationship between the MRI scan on the left and the segmentation mask on the right-hand side. Okay, so here's just an example of the data distribution. So for a point of reference, the normal kidney volume is around, or shall we say, less than 500 milliliters, a lot less. It should be around 200 milliliters for an adult. So you can see these kidneys are very enlarged, and there's a really extreme case here, just one patient over here in the far right that may be considered an outlier, which had extremely large kidneys. Okay, this is the fully convolutional network, or otherwise known as a 3D UNet or VNet for volume net. And Dr. Sujit spoke about this in his presentation, his keynote presentation on the website. But essentially there are two sections. There's a downward section, which is known as an encoder. And so concept here is that the encoder extracts low-level features from the input volume. So things like, okay, the early layers will extract edges and dots and shapes, and as the encoder progresses deeper through the network, then these shapes are combined to kind of get an idea of what they are, And then there's the growing path, or the upward path, which is known as the decoder, which it takes the information that's learned in the encoding path and it maps that back onto the same spatial resolution as the input volume. So just to go a bit deeper into these numbers, so we have here on the left-hand side the input 32 frames and 64 rows, and that was the size of the input data, and one channel. So it's a grayscale volume, so there was just one channel. At the first section of the encoder, you can see we still have 32 frames, 64 rows, 64 columns, but now we have 64 channels. These 64 channels reflect different filters of the convolutional layer. So there were 64 filters in this layer. And the BN here stands for batch normalization, which normalizes the weights of each filter to help the learning process. So, okay, I can't go into full details of the fully convolutional network because we would need a lot more time for that. But okay, we can look at the second layer, and you can see here the data size has been reduced. So this is as a result of pooling, so a 2x2 pooling, which essentially compresses the data. So we went from 32 frames to 16 frames, and 64 rows, 64 columns to 32 and 32. But double the amount of filters were used in this second stage of the encoder. And you can see that this pattern is continued. So the data is compressed, but we use more filters. And the concept here is that the data is transformed into more abstract form, and then in the decoding path, the transformed data is then mapped back on to the same resolution as the input. Okay, but I'm afraid I can't go into any more detail than that, other than saying that dropout is a regularization technique that was used to try to make sure that the network does not just learn to remember input to output. It actually has some kind of, it helps the generalization of the model in machine learning speak. Okay, so to test whether the model is any good, we started off with 135 patient scans, MRI scans, and 5 models were trained.
Sorry, 3 minutes left.
Okay, thank you. Okay, each model was trained using a different section of training data and testing data, so we can evaluate the performance of the model across the whole data set. Okay, this hardware system is used. We use a Titan RTX 24 gigabyte GPU and this very nice looking gaming computer. And this is the performance of the model during training. So each model was trained for 1,000 epochs. And you can see that the accuracy is very, very high, but the dice coefficient, which is an alternative metric used for medical image segmentation, was slightly lower. Right, dice coefficient is a more reliable metric for organ segmentation because it doesn't improve with true negatives. So you could have a small organ in an image which contains a lot of true negatives, and you could get a very high accuracy but have 0 dice coefficient. So dice coefficient is a preferable metric here. And this is an example of the trained network. So like I mentioned, at the early stages, we see the edges being extracted, and then as we look through the network, these edges are combined into shapes, and then eventually towards the output side, they get some form and they start to look like the kidneys, and we get the output segmentation mask. And this is the overall performance. So for each of the 5 cave cross-validation, accuracy didn't really change much. The dice coefficient changed a little bit more, but it was approximately 0.8, which is quite reasonable. But I think we can improve on it for the future. And when the kidney volumes were computed using automatic segmentation, we had about 77 mean absolute error, 77 milliliters, mean absolute percentage error, 16%, and the coefficient of determination 0.9. So I would say these results look highly positive, and we're gonna continue developing this model, and hopefully we'll introduce this to the doctors to evaluate on their future work. Okay, so thank you all for your time. That's the end of my presentation.
Okay, example questions. We have 5 minutes for questions. Any questions from, okay, we have questions from the chat panel from Dr. Sujit Pepasan. First one, why did you choose the process only the image size of 64 times 64 times 1?
Okay, that was a limitation of the hardware to begin with. So to start with, I was using an 8 gigabyte NVIDIA GPU, I think what 1080 or 2080. Oh, can you hear me?
Yes.
Yes, okay. So yeah, previously it was due to a hardware limitation that I used that low resolution number of rows and columns. And I did try training. So when we got the 24 gigabyte GPU, I trained the model with 256 by 256, right? But there was no improvement in the accuracy. There was no improvement in the dice coefficient or in accuracy or in the performance of the kidney volume calculation. So, but it took a lot longer. It took many more hours it took more than double the time to train the network with the data with larger resolution. So I think it was it was more optimal to train at that resolution.
Yes. Any comments from Dr. Sujit Pepasan?
Okay. Dr. Jamie, what was the size of the GPU you used in the past?
It was 8 gigabytes. 8 gigabytes, and it could not train a 32 frame model. It had to be 16 frames and 64 by 64 rows and columns.
Because you put in all the images in one go, like
no. The batch size was 1.
Oh, okay. The batch size still 1, isn't it?
Batch size of 1. Yeah, it wouldn't handle more than that. The 8 gigabyte model, but I believe by doing batch normalization, the batch size is less of a factor, I think.
Okay.
Yeah.
And my another question is, how do you plan to improve your network? Because it's like you improve the size of the image, it doesn't help. So which means you have to then improve the network.
Yeah, so, okay, there are 2 options here. One is well, there are a few options. One is to experiment with different network architecture. The doctors have another data set which includes the T2 MRI, but also four other scans, right? At the moment, the last step in this project, we combined the 4 other scans called the Dixon sequence. We combined them with the T2 MRI into a 5-channel image, hoping that, 5-channel volume, hoping that would provide more information that the network could extract. But after trying that, it didn't perform any better. The performance was equivalent. It wasn't significantly different from just using the T2. So we could try to experiment with different network architectures. But I think for the most part, just increasing the amount of scans will show an improvement. Yeah, we got some more data since I did this work, and the performance is looking better.
Okay, thank you very much, Jamie. That's all for my questions. And I think Dr. Sujit has got some questions to ask you.
Yes, many questions for you, Jamie. Yes. Dr. Sujit, ask you, could you explain about the results of figure number 3A?
Okay.
You can go to that figure.
3A.
Yes.
What figure was it? 3A.
No, because your paper have like the figure.
Yeah, figure numbers. Okay, which one was it? I can't recall. sorry, just a moment. Just opening up the final paper. Sorry for this. Paper 3A. Okay, yeah. So I mentioned that there was a very large kidney, right? So in the distribution of the data here, you can see there's one case. This was one patient that had extremely large left and right kidneys. So when we looked at the full data set, 270 cases, so that was 270 kidneys from 135 scans. This is an overlapping green and red dot, which is actually that outlying patient. You can see the kidney volume is the reference kidney volume is very high, but the estimated kidney volume is much lower. So I would, there's an argument to be made that this data is not representative of the distribution of the other cases. Okay, I can hear somebody else speaking. Can you please turn your microphone off if you're chatting in the background? Okay, so that's on the left-hand side. This outlier is present, but in the right-hand side, this outlier and some cases along the bottom, which had 0. Okay, when the algorithm was first run, they had 0. Okay, but I've since actually tuned the algorithm, so it no longer provides 0 for kidney volume for these cases. But these ones that said 0 have been removed, and this outlier case have been removed on the right. So that's why it says anomalies removed. And when the anomalies are removed, the performance is better. But actually, the performance can be improved. These zeros can be removed by tuning the threshold that's used. So if I show you if I can show you the network. Okay, here the output layer, the sigmoid activation function is used, right, for the binary classification. And by default, anything above 0.5 will be considered class 1. Anything below 0.5 will be considered class 0. And I actually tuned that to make it more stringent. So to increase it now, everything above 0.75 is considered class 1. The problem with having the threshold lower was that the kidney regions, in some cases, some severe cases, the kidney regions overlapped and then were accidentally counted as just one big kidney volume. And that's why the other kidney was considered, was calculated to have zero volume. So I think that's the difference really between this figure and the previous figure, the figure in the paper, is that the threshold used for the output activation function has been altered.
Okay.
Okay.
Answer your question?
Yes, so many questions. So we extend your lives for about 10 minutes for asking questions, okay?
Well, I don't want to delay everybody else.
Okay, we have time. Actually, we have time. Okay. So can you ask? Can you answer like shortly to shortening? Okay. From Dr. Sunny, she asked how many of the samples images that you need to train with this system makes the system become more accurate.
Okay, so in this study, we had 135 total scans and 108 were used for training.
Yes.
Okay, recently, I got some more data, as I mentioned. We have 163 scans now. Now, I still need to repeat the k-fold cross-validation with this larger data set, but just at first glance, it looks like this is going to improve the dice coefficient by about 0.5. So it's getting closer to 0.9 dice coefficient than 0.8. So I think if we have 200 scans, 200 volumes, it should be possible to achieve a dice coefficient of 0.9. using the same model, using the same procedure, just with 200, I think would be a good number.
Okay, so the next question is from Professor On Chin Sen. He asks, may he know if this technique can only be used to detect the volume? What is the limitation?
The limitation.
Yes.
Okay, one limitation is, as I mentioned, this is just semantic segmentation. So it just classifies kidney and non-kidney. It doesn't automatically do instance segmentation. That has to be applied afterwards. So if the two kidney regions overlap, they will just be automatically classified as one kidney. Okay, so it's essentially one weakness is, or one limitation is that this model does not perform instance segmentation. So it cannot separate between left and right kidney because it just uses a binary segmentation mask, 0 or 1. But it's quite straightforward to separate them because they tend to be in the left and right sides. So if the center of mass of that volume is in the left-hand side, then okay, we say it's the left kidney, or actually we say it's the right kidney. And if it's in the right-hand side, we say it's the left kidney.
Okay, so for another questions from Dr. Parinya, why 3D unit was selected in this research? And another question, did you try another architect like Deep Lab V3 plus something? Can you see in the chat, please?
The chat.
Yeah, in chat.
I cannot see the chat. Sorry.
Yep.
Okay. Oh no, I see.
Can you see the
Okay.
chat?
Oh, DeepLab V3.
Yes.
Well, I didn't try DeepLab V3. I previously used a 2D unit for one of these grand challenges in medical image segmentation. So some people might be familiar with the website grandchallenge.org, and I used a 2D unit for that. And I saw, okay, I didn't win the challenge, but I saw the top entries all used a 3D unit. So then I made it my intention to apply the 3D unit to the polycystic kidney disease segmentation. And yeah, it's true. I haven't explored using other architectures. Something maybe to look at in the future. Thank you for that. Thank you for that question.
Then another question from Dr. Subit. How the all data include anomalies or significant disease observations?
Well, okay, so I've kind of explained the anomalous results. Yeah, one of them, the reason some patients had kidney volumes predicted as 0 was because the pixels were overlapping. So the pixels classified as kidney were touching. So then it was just classed as one big kidney, and then the other kidney was classified as 0. But that was corrected by adjusting the threshold of the sigmoid activation function at the output. And the other case was just a very large, must have been a large person with a very severe case of disease. So I think it's quite a heterogeneous disease, and patients can present in various symptoms. Some have many small cysts. Some have like one very large cyst. And I think this is partially due to the genetics of the disease. And yeah, I think maybe a larger data set will help to overcome issues about anomalies in the distribution.
So the last question is from Professor Nantachai. He asks, can you apply your algorithm to other input, such as other information, other images? Yes.
Yeah, it's possible. Yeah, I mean, essentially, this same model has become a de facto standard for medical image segmentation, and even for other images. So satellite images, segmenting fields in satellite images is possible. All that you can identify the pixels in an image or the voxels in a volume that belong to a particular class, provided that you have many examples of the image, or for the 3D case, the volume with the segmentation mask or the labels. You know, you have the pixels all labeled 0 or 1, and then you can train the network to do pretty much any type of image. You know,
Yeah.
provided you have enough examples, I think.
Response times or system. Okay, for the last question from the third side. He wants to know the response time of the systems.
Yeah, oh yeah, I saw that. So to make a prediction, so if you're using the model to make a prediction on an individual case, it might take 1 second, 2 seconds, but you can do continuously. You could make it predictions for many cases at one time. So essentially, the time it takes is negligible considered to the time it takes for the doctor to make the segmentation. So doctor might take 30 minutes or so, but the model is just almost instantaneous.
And okay, we will have go to the next presenters. Okay, thank you so much,
Okay.
Dr. Jamie, and thank you for many questions. So
Thanks
interesting.
everyone for the questions.
Okay, thank you.